Right, so this is the title. Obviously, we all know that irrigation of the root canals is a very debated question in endodontics. And what I thought of is designing a mathematical and computational simulation to determine the time required for sodium hypochlorite to dissolute all the pulp in the canal. So this basically looks at vital cases where we have pulp in the canal, but also necrotic cases, because we still, in any cases, we still have pulp remnants in the canal, and we do want to get rid of those. Why do we want to obtain tissue dissolution? Because there are many studies, and very early studies, that show the inability to remove mechanically the entire content from the canal. So, as you can see, quite old ones. Also, we don't want to leave any pulp remnants because they promote bacterial growth and can produce post-operative pain. And why did we choose sodium hypochlorite? Because it's capable of tissue dissolution. There are other substances that are capable of tissue dissolution, but they haven't been well investigated and obviously not used in endodontics. One of them is chlorine dioxide. That was a bit investigated, but not too thorough. Why do we want to perform irrigation? Because we want to bring the solution of sodium hypochlorite in the canal, and we've got to get it in contact with the pulp remnants. And obviously there is a flowing process that takes place, which is very important, because we may irrigate, but if we don't have a solution with adequate properties, and we don't use a velocity adequate, or the shape of the canal, it's not proper for flowing, then we won't bring the solution in contact with the tissue we want to dissolve. What are mathematical models and where are they used? They're used in very well in many domains. Probably the most well-known is the weather forecasting model, and all global weather is forecasted according to mathematical models. But they can also be used in any other domains where physical and chemical processes occur. How do they look like? Well, we've got to think what we know, and we've got input data, and then there is a string of equations that characterize the phenomena. I mean, a physicist knows all the physics laws and can investigate and can put everything in writing, and we get results. I will show you part of how it looks like, but there is, don't freak out, because at this point computers help us a lot, and we've got the MathCAD software where all these equations go, and then we input the data and get the results. So what you've got here is only the string from number 14 to number 20, but it starts with 1, obviously, goes all the way to 37. So. And that's only the processes that take place. There's also a mesh where we design the system where the process takes place. So basically the mesh is the root canal, the syringe, and the needle. I'm not sure whether you can all see, there are some sizes there that will be a bit small. How did we collect it? How did I collect those data? Because obviously we want to input something that's relevant. I carried out a literature review and sort of come up with an average diameter of the apical foramen, average diameter of the accessory canals, the most frequent position where the accessory canals are. There are many papers, I didn't list all the papers there. Also, what's the average taper of the prepared canal? What is the flow speed of solution from syringe and needle, obviously, because this is all about syringe and needle. No ultrasonic activation, no other things involved, just syringe and needle. What's the most efficient needle design? Right, what's the speed of tissue dissolution? Do we know that? We know that the soft tissue immersed in sodium hypochlorite disappears, so it's dissolutive. But how fast does it happen? All the studies we had so far, and I looked at, they were all immersing pulp tissue in sodium hypochlorite. This is not exactly what happens when we insert the needle in the canal and we carry out the irrigation. It's a totally different process. And that's paper. Also, of course, the speed of dissolution depends on the agitation of the solution. How fast does it move and how fast does it come in contact with the tissue. Also, we all know the root canal is a very limited space. It's not, like I said, not the same process as immersing tissue in solution. So we need to know the speed and pattern of dissolution. Also the flowing rate of the solution in the canals, but that has been addressed before by other mathematical models, so we know a bit about that, but also what we've done comes up with our own flowing rates and all that's involved. So we needed to carry out some experimental measurements, and we've experimented on collagen samples because collagen is the most difficult component to break down on the composition of the pulp tissue. So this is how the collagen breaks down. We've got the collagen fibers. They're made out of fibrils and then tropocollagen and amino acids. So if we manage to break down up to the amino acids level, they are dissolvable. And even the fibrils and tropocollagen, they are kind of dissolvable and they can be carried away, flushed away by the solution. And these are some microscopic photographs of how the hypochlorite attacks the collagen with the time scale. Very interesting to notice that the attack happens in clusters. You can see the clusters on the top figure, and they get flushed away, those clusters. And also, the other figure, you see the collagen fibers, they're smaller and obviously they don't break down completely. It doesn't get to the stage of amino acids, so some of the small fibrils, they get flushed away. And there is an experimental apparatus involved to work out the parameters of dissolution of all the collagen samples. Looks like this. So you see what happens. Obviously in the middle there is the solution of hypochlorite. This is all done with 1% solution, but given the mathematical model, it can work out what happens with other concentrations, so not necessarily only 1%. This is a little movie. Obviously, this doesn't work because this should have shown you how the solution spins around. So this is an agitated solution, but this is a little moving and it doesn't. You?
Can right click?
Yeah, I'm trying.
No.
I mean, it worked on my computer. Obviously,
So
one of those things.
Maybe because the movie file, what is it? It's there in the computer, right?
Probably. Anyway, I can email you the whole movies on the YouTube. It's 3 minutes or something like that. We didn't get to film the whole thing, but because we ran out of memory. But you can clearly see what happens with that sample. That was just a sample of soft tissue. So we know how fast that solution spins because we can work out how it spins, and these are the results. This is only one of the tables, there's more of them. We put them on. And obviously after we solve the mathematical model, it comes up with the graphical representation. This is not the best of them, but this is the first. And it's a 3-dimensional image, if you see. Maybe the next one will make more sense. So, where you see the color change, that's where the dissolution process takes place. That's where the mass transfer takes place. And you can see where it starts, you can clearly see where it ends, because after that, when it ends, it all stays the same, so nothing gets dissolved any longer. So,
The ends, 10 minutes.
yeah.
You can go
Another
with
one
that.
similar to that one, but different parameters. Another one. And the results, I mean, these are only preliminary results. The experimental measurements that were accounted for in the preliminary results, that was just a preliminary model to see whether the whole thing works out. But those will be inputted in the model and we'll get some results. And according,
You have the experimental control. So these were to
It's-
see the system is working.
it's not a control. It's
to check
just to
the-
determine some parameters, the speed and pattern of dissolution. Right, so that's, like I said, it's still working in progress. And thank you for listening.
Thank you very much. Thank you, Diana, for the
Questions?
presentations. Yeah, time for questions. So these are actually the ones, I mean, not the experimental control, I mean your solution compared to a control. I mean, it's actually testing the system if it's actually working or not.
Well, all the results you've seen that
Yeah.
I've put here, they're all just to test the system, whether it works. And
Because
some of the data are sort of based on the literature, on all the studies made by immersing pulp into solution, sort of kind of guessing at the beginning what the speed of dissolution will be and how does it evolve. There are some very, very interesting results. I mean, it appears that temperature plays a major role, more than the concentration of the solution. So that will be an interesting result, because obviously when you can use a 1% solution at a slightly higher temperature, and you don't need a very high temperature, 37 degrees will do, you get a much faster process. So,
And that's actually linking to your study. How many they heat activate?
31%.
Okay.
yeah, so not too many people.
The-
I must admit, I didn't thought that heating the solution, and maybe also because of convenience, I didn't heat it up, but now I'm thinking more and more I should sort of introduce it in the clinical practice.
So you're looking at the time needed for tissue dissolution, right?
Yeah.
Comes into
Yes.
contact. So how would this model correspond to the actual tooth when it comes to the flow of irrigation? Obviously, the model had a lot of irrigation compared to what it would be in the actual tooth. And
No, the model should mimic exactly what happens in the canal, because we know how fast we inject the solution. We have this data, we know the flowing speed from a syringe and needle. It has been measured before.
I see, so it's been already
Okay, but obviously, the way the solution flows in the canal, the speed doesn't stay the same, because it's highly influenced by the shape of the canal, by the walls of the canal, by I mean, yes, it's a complex process. So obviously the speed doesn't stay the same. It varies, the further it goes, I mean, the further away from the needle tip, the slower the speed. Obviously, when you don't get flowing, then you don't get dissolution.
So your spinning is actually at the speed where the solution leaves the needle. Is it
No,
the same?
that spinning is at a different speed. But you can, well, from a physicist's point of view, when you know speed of dissolution at a certain speed of agitation, when you can work out what happens if you lower that speed a lot. If you have a different speed of solution flowing, you can still work out how fast the dissolution happens.
Just ask a question. In my reading, okay, there's something called vapor lock. I'm sure you've heard of it, where in clinical you get basically a small
Yes.
epical area of
Yes.
a gas bubble,
Yeah,
and
Yeah.
all the research is showing that you can't get rid of it by irrigating. You have to either wait for it to disappear, or there's
Yes.
only two ways that they've actually shown that it goes, either by getting a GP point and going right down to the apex,
okay.
okay, or using the endovac, which is the negative suction, to draw
Yes,
it out.
I think I know all the studies you
Yeah.
speak about. They're all very much
On that
empirical.
one, yeah.
I'm not sure what they say there really happens. One of them is done on a macroscopic model. They looked at a very huge pipe, and what happens in the pipe, it doesn't apply to flowing in such small spaces. So, no, I mean, no.
So it-
We didn't
My,
thought that would be
the reason I asked the question
an
is that
issue.
my reading of it was that because of this few millimetres of vapour lock, well, when we think that we're syringing
But-
down there, we're not actually doing it.
From my point of view, and looking, maybe I missed this one, but I didn't thought there was any reliable evidence of that.
Of vapour lock.
Yes,
Okay,
yeah.
I'm sure you said read it.
Yes,
Yeah,
yes,
yeah.
I heard of it. It's the chow, isn't it the chow paper?
Yeah,
But that's
yeah.
done on a macroscopic model, a huge thing. It's a totally different thing, and it's very empirical. So,
Okay, right. Different interpretation, different studies. Yeah.
What needle do you use?
it's a 27 gauge.
Is it end? Or is it
It's
side
a
venting?
side-vented needle, because previous studies showed that it's the most efficient design. And obviously, that wasn't the scope of this study to investigate further whether that's real or not.
I mean, I don't know anything about mathematical models and the depth that you showed, but can you add bits onto that model to
You can have, actually,
bit of
the
sonication,
temperature,
temperature?
sonication will be a bit of an issue. But the temperature, that was added, the last thing to be added, and it made the whole thing a little more complex. But basically what you can get with that is you will get a wide variation. What happens with concentration started from 0.5% up to 5%? What happens at different temperatures? How fast does it happen? And obviously you can come up with some very interesting conclusions.
Thank you very much, Diana, for the
Wow.
presentation. Good luck with the day.